Hi, these are the lesson activities for section 2.2 for Math 204, differential equations. Consider the system of differential equations. dx dt is 0 and dy dt is y. We're going to write this system using vector notation. P prime of t equals x prime of t, y prime of t. Okay, so P prime of t is going to be 0, y. That's x prime and y prime. On the left below, sketch enough vectors. Vectors have a direction and a magnitude in the vector field to get a sense of it. So we're looking at the xy plane. And we're going to plot points 0, comma, y. So at each point, x, y, we're going to draw a vector in the 0, y direction. Okay, so at 0, 0, we have no vector. Then let's see. 1, 2, 3, 4. So we just pick some xy points. So maybe 1, 0. So this right here, 1, 0. So at x, y equals 1, 0, my vector, P prime of t, is always 0, and then y is 0 also. So all along the x-axis, we just have points, okay? The vector is 0, 0. Okay, let's try 0, 1. So P prime at the point 0, comma 1, when x is 0 and y is 1, you always have 0 because 0 is the first entry, and the second entry is the y coordinate. So if we're at 0, 1, the y coordinate is 1. So right here, I'm going to draw a vector in the 0, 1 direction. So over 0, up 1. So there's my vector. Maybe I'll actually do my vectors in a different color. Okay, and then I'm going to choose the point 0, 2. So my vector, P prime, would be 0, then the y coordinate, which is 2. So that's going to be a vector over 0, up 2. And then if I did 0, 3, that would be over 0, up 3, so a longer arrow. Okay, so there are a few vectors to start. Okay, let's look at 1, 1. So P prime would be 0, then the y coordinate, which is 1. So it looks like this. And then at 0, 2, it would be 0, 2, and then 0, 3. Okay, I'm starting to see what this looks like. Something like that. And then if I did some points below the x-axis, like 1, -1, when x is 1 and y is -1, the P prime vector would be 0, -1, so it would point down like that, and then 0, -2, and then 0, -3, like that. Okay. And then on the right, we want to sketch the associated direction field, which is going to look exactly like this, except we're going to scale all of our arrows down to a length of 1. Okay, so these are all arrows with a length of 1. Something like that. Okay, so now we want to give a rough sketch of the phase portrait of the system. The phase portrait captures equilibrium points. So that's the line of dots along the x-axis, all these equilibrium points. Okay, and then if we just follow the direction field, which has up arrows above the x-axis and down arrows below the x-axis, we just draw in several curves, lines in this case, to indicate the pattern. Okay, so all of our solution curves look like these up and down lines. All right, and then it says, mark the point on the phase plane that represents x of 0 equals 1, y of 0 equals -2. So that's an x and a y coordinate. So 1, -2 would be like about right here. Okay. And if you haven't already, draw the solution curve in the phase plane that satisfies the initial condition. So we have already, because it's right on this purple line here, but that is the solution. Using the solution curve in the phase plane as a guide, sketch on one set of axes the x of t and y of t graphs that satisfy the initial condition given above. Okay, so I'm going to draw it up here. So x of t and y of t. So this is t and this is x and y. I'm going to draw them both on the same set of axes. And my initial condition is 1, -2. X of 0 is 1. So I'm going to try to draw x first. I'll do x in orange. So x of 0 is 1. So I'm going to plot that. When t is 0, x is 1. And then I want to look at the phase portrait and say, okay, if I'm starting here at x is 1 and y is -2, and I follow the solution curve, it's just going down like this. And what's happening to the x coordinate as we move down this line? The x coordinate is not changing because the x coordinate is right and left. So x just stays 1. Every point on this line is 1 comma something. So x just stays 1 forever. So x of t looks like that. Horizontal line at 1. And then y, let's see, I'll do that in a different color. Y will be green. Okay, so for y, we start at this point here. Y starts at -2. So let's plot that. -2, that's my initial condition. And then from this point, we follow the curve, we follow the arrow, and it's moving. What's happening to y? It's going down. It's getting more and more negative. Okay, so my y coordinate, I don't know exactly how. It's going down to -infinity, so it's decreasing. It's not asymptotically decreasing to anything. It's going to -infinity. So it's hard to know exactly what this looks like. Could look like that. Could look like that. Could be a straight line down. There's lots of ways to draw it. We don't know its exact shape, but I'm just going to pick one so that I don't confuse myself. So I think it's going to go something like that, just down. It's hard to know how fast because we took the vectors out, right? We took out the length of the vectors, which tells you how fast this is moving. If we go back and look at the vector field, which is on the previous page, you'd see that the vectors get longer and longer and longer, so it starts moving faster and faster and faster. So that's why I drew it with that concave down shape. A direction field for the given system is shown. Mark the point on the phase plane that represents x of 0 equals -1 and y of 0 equals 1. So that's an x coordinate and a y coordinate. So -1, 1 is a point because this is the x, y plane. You can't see time in here. So we just have the x and the y value. We know it's at time 0, but the x and the y value at that moment in time are -1 and 1. So I plot -1, 1. There we go. If you haven't already, draw the solution curve in the phase plane that corresponds to the initial condition. So it looks like we just follow the arrows and they go like that. And it looks like it came from this point right here. Like if we go backwards in time, it came from there. And if we draw the whole solution, it looks like that. Using the direction field, sketch several additional solution curves to obtain a phase portrait. Okay, so this point is really important. It looks like an equilibrium point, or a source where everything is coming out of it. So if I draw some additional solutions, they look something like this. I'm just randomly following the arrows here. Something like that. Oh, and I should do maybe a couple more over here. Okay. So that's a phase portrait. What are the equilibrium solutions for this system? It looks like it's at 1, 1. If you haven't already, indicate the equilibrium solution in your phase portrait. Okay, it's already drawn in there. Using the solution curve in the phase plane as a guide, sketch on one set of axes x of t and y of t graphs that satisfy the initial condition given above. Okay, so I'm going to draw it next to the phase plane so that we can refer to it as needed. Okay, so this is t. And let's see, I'm going to do x in orange. Okay, so x of 0 is -1, so I put -1 on here as my first point. And then I'm looking at this initial condition here. This was my -1, 1 initial condition. And as time moves forward, we just follow this curve. So it looks like the x coordinate starts at -1 and moves left. So it gets more and more negative, okay? So the x coordinate is decreasing to -infinity. So x is going to do something like that, okay? And it looks like before -1, it was decreasing and it started at 1. It started from an x coordinate of 1 and then decreased. So let's see, maybe I'm just going to fix this a little bit. Here's 1, about right there, and it's going to go like that. So that's sort of it's an asymptote that it came from, and then it's just decreasing to -infinity. All right, and then y, I'll do in green. So y starts at 1, and as I follow the solution curve, the y coordinate is not ever changing. We're staying on this horizontal line where the y coordinate is always 1. So forwards and backwards in time, the y coordinate never changes. So there are my x and y solution curves. Note that both equations in this system are linear, so we're going to solve each one independently to obtain a general solution. We'll use lucky guess from 1.8. It's pretty easy because you can use an equilibrium solution as your particular solution, and those are pretty easy to find. And then we're going to use the initial conditions to find the particular solutions to the IVP. So how does your analytic solution compare to the graphs from part F? All right, so I'm going to just put these over here out of the way. I have to solve both of them. So I'm going to work on dx dt first. So dx dt is x minus 1. So step 1 of lucky guess is to solve the associated homogeneous equation, which is just dx dt equals x. We can solve this by separation of variables, or if you've done it enough times already, you probably recognize that the solution to this would be x equals c e to the t. That's my x homogeneous. Okay, step 2 is to find an x particular. We, in previous problems, have always used our lucky guess, our way of guessing x particular, but sometimes, like in this case, there is an easy particular solution to find, the equilibrium solution, which you find by setting dx dt equal to 0. So we get x equals 1. So the constant solution, or the equilibrium solution, is x of t equals 1 for all time, and that is my x particular. So my step 3 is to add these together. X general is x homogeneous, c e to the t, plus x particular, 1. And then we solve for c by using the initial condition that x of 0 equals negative 1. So x of 0 would give me c plus 1, and that's supposed to be negative 1. So c equals negative 2, which means that my solution, x of t, is going to be c e to the t plus 1, but replace the c with a negative 2. Negative 2 e to the t plus 1. For y of t, we have dy dt equals y minus 1. This is the exact same problem we just did. We just renamed the variable x instead of y. So we have the exact same solution method. So step 1, we get y homogeneous is c e to the t. Step 2, y particular is going to be 1. And step 3, we add them together to get y general. So c e to the t plus 1. And then we use the initial condition that y of 0 equals 1. Y of 0, that would be c plus 1 equals 1, which tells me that c equals 0. So my y of t solution to the initial value problem is going to be c e to the t plus 1, but c is actually 0. So 0 e to the t is 0, and you just get y of t equals 1. These two functions, if you were to graph them, look just like the functions we graphed on the previous page when we did this qualitatively.